should have said last time, so I'll start with those. So one of the things I did last time was I mentioned some problems that were open for n by n random matrices, and I assumed these matrices were real and symmetric, and stated the fact that if you didn't have sort of Gaussian entries, for which you know GUE statistics, of course, we had some other reasonable entries that were random and independent, then we did not know anything about the universality. Oh, yeah. Is this on? Or do I need it? But there are some very nice universality results for GUE random matrices, n by n systems, and this is due to Kurt Johansson, and there is an issue about whether he could do something with the nature of the eigenstates. I don't know. Leonid and I had a little discussion about that a while ago, and I asked Johansson whether he knew what the inverse participation ratio of a perturbed GUE system was. He said he did not. I was surprised that he knew about the GU, but the level statistics were universal, but he could not determine anything about the eigen functions, or he probably hadn't tried. I suspect maybe you could do that. So there is some reasonable mathematical work here. The other thing I wanted to focus on, which is, we always talk about. I've been talking a lot about time evolution, and I'll do a little bit more of that. And so one conjecture which I think is in some sense physically obvious, but mathematically I believe quite non-trivial, and that is to show or prove, even show, but I'll say prove, that if I look at any system r squared of t with randomness, and I take the expectation that so if it were diffusive, I would have a bound of this type. Okay, I would have r squared would go like t, that would be diffusion. And all I would like, so of course we expect many systems to be diffusive. But with randomness, you don't really expect to see superdiffusion. So how could we show something of the following modest kind? 1 plus delta here, where delta is positive and small. So in other words, show that you cannot, if you can show such a thing, you cannot have superdiffusion. And even if you like to say, it seems absurd to ask this question, how do we know that in 2 dimensions or in 3 dimensions, your motion isn't, how can you really prove without resorting to some high-powered perturbation theory that your motion is really strictly subballistic with some reasonable delta there? So these are questions which are not known. And if we did have the answer to a simple sort of question like this, which you would think was obvious, it would give you a lot of information about Lyapunov exponents, about decays about average Green's functions. So it's it's a useful thing to know if we could do this. So this is a big question, I should emphasize. Okay, now today I'm going to talk about some of the mathematical results and some of the mathematical tools. So there are basic tools, many of which you've seen, I'm sure, but let me just review the basics. The basic tool in all of this stuff, as I'm sure you've heard from a number of speakers, is the Wegener estimate. And that tells you that if I pick an energy here and I have a box, the probability the distance of E, so I should have a distance here, of E to the spectrum of H lambda, where H lambda is H restricted to the box. The probability this is less than delta is less than some constant times delta times the volume. And that's just the volume of the box. So that's, without that, or an estimate like that, we have a lot of trouble doing any kind of mathematics. And unfortunately, there are plenty of examples where we don't know this estimate, and Bernoulli would be one of the basic cases. But we do. This is basically step one. You have to have some control over the density of states, and the better control you have, the more you'll be able to say later on. And so it is, especially in, let's say, for random contexts. Of course, we know this, but one could look at, other systems in which you have a cocycle or you have something else, and you would like to understand some kind of regularity of the density of states. It may not be Lipschitz as I have here. In other words, this could be the square root of delta. That would still be pretty useful. But if you knew things like this, you would understand all kinds of things about chaotic behavior of even nonlinear systems if you really understood how the density of states behave. So it's an extremely important quantity. We take it for granted here in the context because Wegener has this very beautiful proof of it. But once you have some more complicated system, nonlinear system, and I linearize around it, then this kind of estimate is far from being understood. And if you knew it and you use the Fowler's formula, you would get lots of information. So that's so the second thing, which of course, yes.
We're not given exactly this formulation. So how does it? Maybe suppose I'm worried about atoms.
Yes.
Use Leonid Pasteur's.
Right. How
does this eliminate? If I have atoms.
This is not. We don't know how to prove this for atoms. We do not know how to prove this for atoms.
So there's an assumption here.
Yes. So the assumption, no atoms. And in fact, my assumption, if you remember, so maybe I should emphasize this again, is that my distribution, G of V, and the lack of atoms has to do with the fact that that doesn't have any spikes in it.
Oh, but I just proved that the density of states is bounded. You can write a line with parts inequality.
Yes. So this is, so you'll have something here, density of states here times delta times volume. Is that what you want me to write, Leonid? Or yeah, good. Thank you. And so our knowledge of density of states is, I can go on about this, but maybe I should move to the next step because there's lots to say about that, and I'll have something to say about it later. So, so that's one. So I'm going through some mathematical tools here. One is the other basic one, which arises all the time, is of course the resolvent identity. And I don't know that I have to write this down. Or maybe I should, at least in simple cases. So let's suppose H is equal to H0 plus H1. And you can think of H as being our random Schrodinger, if you like, a random potential. But H0, sometimes people like to think of H0 as being Laplacian. Sometimes they like to think of it as being the potential itself. So how you choose H0 and H1 is up to you. How you make this decomposition is your choice. And the choice is very important, and it can vary from context to context, or even within the same context at different places in space when you do perturbation theory. So let's pick an energy E, epsilon equal E plus I epsilon, and form the following Green's function. G0 is just H0 minus E epsilon. And similarly, G is the same thing. Epsilon, put the epsilon in here. So these are matrices or operators, if you want to think of them that way. And then the basic resolvent identity, which is the basis for so much of perturbation theory, and is simply this. This is, G is equal to G0 minus G0 H call it H1. There's my perturbation theory times G. And that's all. But how we choose the H1 or the H0, either way, is going to be very important. So this, by choosing H0 properly, you may include self-energies and things like this, which I will try to illustrate. So that's the basic resolvent identity, and I'll spend some time giving examples of how we can choose H0 and H1 in an interesting fashion. The second thing, which is not quite as important, but it's a very useful thing. So if those of you who don't know it, it's probably worth learning. It's simple enough. It's the famous Combs-Thomas estimate. And let's imagine that my Hamiltonian is just the Hamiltonian that we've been working with, discrete Laplacian plus random potential. It works in a much broader context, but let me not try to be general here. So now let's suppose we have H. We could have H, and we can have the H in a box, even if you prefer to have it in a box, but it doesn't really matter. You'll see the idea is very simple. And we look at the spectrum of H. And then we'll suppose that the distance from E to the spectrum of H, and E can be some complex number now, some complex guy. Okay, we look at distance from E to the spectrum, okay, and we'll suppose that distance, just measured in the usual distance of numbers, we'll suppose that distance is equal to kappa, just by definition, okay. Then of course E is outside the spectrum by this amount kappa, and it won't surprise you to learn that the Green's function, xy, should decay exponentially fast, and the bound is basically by some constant times kappa, which I won't be too precise about, times x minus y, divided by kappa. Okay?
In any dimension?
In any dimension, yes. The constant may depend upon dimension, but it's a fact. Okay? So if you're outside the spectrum, we all know it decays, and this tells you precisely, and you can actually get this constant, you compute this constant quite accurately if you wish. There's a slightly better estimate, so I'll put that on the board too, and I'll just indicate the idea of the proof. It's a fairly standard in math physics literature, so I won't go into it, but the idea is very nice, and so I will at least mention that. So there's a stronger version, and that's suppose that E is actually less than the spectrum. In other words, suppose that the energy lies below all the spectrum. So I'm below the spectrum. Then you can get the same estimate, and it says that E to the minus some constant. But this is a better estimate because I'm thinking of kappa as being small. Okay, I must say I'm thinking about kappa as being small. Yes?
So, you mean like the real part?
Yes. I'll assume E is real now, let's say, and lies below. Yes, it's probably important that I think if I make this is not real, I'm probably in a little bit of trouble. So I'm going to be below the spectrum, below the bottom of the spectrum. Okay. Then what would you think you get? Well, if you computed the Green's function for Laplacian plus m squared, you know you get a square root of m, right? So you will get the square root of kappa. Okay. Divided by kappa.
Sorry, would you mind repeating that argument?
Sure. So the first one just says I look at the distance from the energy, which may be complex, so I might have an I in it, to the spectrum. Okay? And then I call that distance kappa. I just take the magnitude of that distance. And then if I want to compute the decay for any x and y, this is valid for any x and y, then I will get exponential decay, and that decay will depend upon kappa, and the kappa is just that. Sorry, the lower one. Okay.
Why you got the square root?
Why the square root? Because this is actually below the spectrum, and that makes a difference.
Again is kappa. You're not writing about
Sorry.
Again, kappa.
Kappa, same kappa. Sorry. Yes. This is the same distance.
Yeah. First case could be between two
Right.
bands.
Right. Yeah.
But now it's really on the far left.
Yeah, yeah.
And then we
Far
get-
left or far right. Probably you can do it even with bands, but you have to be a little bit more careful. And so you use the fact that, so we all know this fact from, if I look at 1 over Laplacian plus m squared, well, m squared would be my energy, right? This is a positive operator, and we know we decay with the square root. So this is just a generalization of that statement. But if I pick my energy inside my band, I will get this. Near the edges, or if I pick E plus I epsilon, I will get this kind of decay. So it fits with what you know from Fourier analysis, except you don't use Fourier analysis. Yeah, okay. So why is this true? I won't go into the proof, but you can prove it yourself once you know the trick. There is a trick, of course.
There is a question.
Yes, sorry.
I didn't get this before.
Yeah, sorry.
This E in the second, the stronger version.
Yeah.
Should this E to be real or?
Yes, I'm sorry. I should write it down. I don't know what will happen if I don't make it real, so I won't say.
Can you get the absolute value of it?
I beg your pardon?
Can you get just absolute value of the same E?
Yeah, the same. This E should be below the spectrum. Okay. Yeah, it should be below the spectrum. Okay. And then the claim is that the Green's function. This has nothing to do with randomness. Okay. I mean, it's true for any realization of the potential. It's a general fact. There's no averaging here or anything, right? I am on a lattice. I'm going to use that. And then I'm telling you that the Green's function will decay exponentially fast with a square root rather than the regular energy. Okay. And as I said, if you just compute the Fourier transform of 1 over Laplacian plus m squared, you know that has a length of m, and that's what I'm pointing out here. The difference is this square root. Yeah.
This is probably true only for the continuous version.
This is lattice.
This is lattice.
This is
Why
lattice.
there is no symmetry?
And there's a kappa is small.
Why there is no symmetry between the upper spectrum?
Yeah, because I didn't bother to put it in. You could do the upper one too.
Okay.
You could do the upper one too.
So
And there are versions of this in the continuum. If you want to do it in the continuum, you have to be a little bit more careful. You can do it in the continuum. So let me just say what the idea is, okay? Because I don't want to spend too long on this, but it's a nice theorem. So anyhow, before I go on, I guess I should make sure you understand the statement I'm making here. So any questions about the statement? Okay. It's just telling you that Green's functions decay when I get outside the spectrum. And if I'm so fortunate to be below the spectrum, I get additional decay. I get better decay. And as I'm saying here, you shouldn't take this too literally unless kappa is small, and then it's really correct. Okay. There's a similar statement when kappa is large, but then I have to put logs or something funny in there. I don't want to do it. So the important case is when kappa is small anyhow. So this is the Combs-Thomas argument, and you can use it in many, many contexts. You can get decays of Green's functions in all kinds of things. And the idea is very simple. The idea is what we sometimes call just conjugation. So I consider the following guy, e to the ax, my Hamiltonian, e to the minus ax. Okay? Now if I write this out, you see the potential doesn't see this conjugation. It just moves right through it. And by e to the ax, I just mean you multiply by e to the ax and multiply by plus e to the ax. And so you will, of course, start off with minus Laplacian plus v, lambda v. Then there'll be corrections. If you compute it, you'll get an a gradient minus a squared, something like this. Maybe there's a factor of 2. You'll get something of this type. You can do it in the continuum, if you like.
A is Hermitian or?
A is just a scalar. Just a scalar. Nothing fancy here. And I will need to get this result, I'll need to make the A somewhat smaller than this kappa for me to do the job. Okay? So you choose A, absolute A. You can choose it either sign, but you must make sure it's less than, let's say, kappa over 2. Okay? So you just conjugate. And of course, if A is small, you see, this is going to be small. And you can prove, let me call this new operator HA. Then you can prove that the new guy, GA, yeah, xy. Well, this new operator, which you've gotten by conjugation, is less than 2 over kappa as an operator. And then this follows. Okay.
Is the gradient just a derivative there? Or is
Yes. It's a finite difference derivative.
I
It's a finite gradient. So what am I doing? In momentum space, I'm just taking p and I'm adding IA to it and expanding.
Okay.
Right? That's what that is, roughly speaking. And so I'll get a minus a squared and so forth. Okay. So this piece here is yeah, I think maybe it isn't. Do I need an I in there? I don't think so. I think that's roughly correct. So that's how you get it. And then you can just check that this operator, which this operator is not the same. It's not unitarily equivalent in any sense, but you can if you want to do it in the continuum, then you should do some kind of analytic continuation in A. That's how it's usually said. But on the lattice, you just do this and you get what you want. So it's a useful fact. Now,
Maybe you should just finish it off and just show them how it gets the exponential.
okay. I will take David's advice. How do you get the exponential decay in here? Well, you can just take GA and you consider the inner product of it with 0 and delta x. Okay? Now the 0 won't be felt by this piece of the conjugation here, unseen. So I'm using the fact that the Green's function is conjugated the same way, right? I just have to invert it. Since I know this operator is bounded because this is relatively small compared to here, then I have this is bounded by some 2 over kappa. But if I write this out, I'll see this is equal to e to the ax, e to the plus ax, right? G x 0. And this has to be less than 2 kappa. And then you just multiply e to the ax over on the other side, and I assume a is positive, and then you get the decay you want. Okay. So the point is, to go from here to here, I just unconjugate what I did, right? And to check that this is bounded, well, you have to be able to invert this piece, which you've already assumed is invertible because of the distance from the spectrum. And then the rest of it is relatively small, so you can expand on the Neumann series or whatever you want to do, and you will get the decay. So this is quite a useful fact. And as I said, you don't have to use this conjugation. You can use much more sophisticated conjugations, and you will get things like WKB or whatever you like to get quite quickly. So the third, let's see, what is the other thing to say? Yes, so the third thing to say is of course, this method that I will describe has to do with some multiscale. And now, to a large extent, you can replace this by what's called the fractional moment method. And we'll see that this is really a consequence of some basically clever use of the resolvent identity, and so I'll say something about that. And then the fourth ingredient is, of course, supersymmetry, which is still not being used very much by the mathematics community, but I believe it is certainly one of the most promising tools for making progress in the area that we're all interested in. And hopefully I'll have time on tomorrow, I guess it will be tomorrow morning, to describe some recent work, which I think will fit in very well with what Jan has been talking to you about. It's a simple model due to Martin Zirnbauer. This is a model, he calls it a toy model, for localization and delocalization. And the advantage of this model is, first of all, it's somewhat simpler to see. You can write it down fairly explicitly. It looks like a regular statistical mechanics model, except it's got some determinant in it, needless to say. And in this model, you can see localization, delocalization. So for example, suppose you want to understand why 2 dimensions is localized. Well, I can't prove that to you in this model. I'd like to be able to say I could, but I cannot prove it to you. But what Margarita and Martin and I have realized is, at the very least, there's a saddle, and you just do a saddle calculation, and you will see that there's a very special saddle in 2 dimensions, which gives you this extremely long correlation length, localization length. In 1 dimension, of course, it's as you expect. And in 2 dimensions, you will even see, 3 dimensions, you will even see the mobility edge transition. And it's all apparent from a simple saddle calculation, which is reminiscent of what you see actually in the classical, these large N models of COTS, and I guess they're called, what they call a spherical model. Yeah, very similar. Okay, so I don't know that I'll ever really get that far, but that's my goal. So now let me go to the resolvent identity and see what we can do with it, and see what its power is. And so the resolvent identity, we're going to use it. Hopefully, I'll have time to use it a couple of ways today. Once to generate perturbation theory, in particular ladder diagrams, and even indicate how cross ladders occur. And secondly, to give you a finite volume criteria for localization. So it's so here's the one of the forms of the resolvent identity I want to use. So as usual, we will take H to be minus Laplacian plus lambda v. And now I'm on the lattice, so I'm going to pick a domain. It doesn't have to be a square, but often it will be. So this is a domain, a bounded domain. I'll sometimes call it B. This is its complement. Okay. And what I want to do, so I forgot the potential in here. And I will look at E. I'll look at the Green's function at some E, which is E plus I epsilon. So what I want to do is to rewrite this Hamiltonian as follows. I'll write it as minus Laplacian. H0 will be minus Laplacian with Dirichlet boundary conditions along this line here. In other words, I'm going to decouple this region from this region, and so maybe I'll indicate this by a sub gamma, and the gamma here will be this boundary of B. I'll call it gamma. Okay. So this Laplacian will break up into a piece. It's a direct sum of the Laplacian inside here and the Laplacian in the exterior. So it has 2 parts to it. And then we'll add in the lambda v. Now, the lambda v doesn't couple these 2 sides, so I don't need to bother with that. And then my perturbation, which I call h1 before, will just be minus what I'll call this operator gamma. It's the boundary operator. And the boundary operator just means that gamma j prime equals 1 on the boundary of B. So if I indicate it on the board like this, j prime, or in the inverse order, that's 1 on the boundary, and it's 0 otherwise. Okay, so that is the decomposition I want to choose. So what I've done is I've deleted all the boundary connections, all the hoppings between these points along the boundary, and then I've put them back in. Okay, so it's a trivial identity, at least if I have my signs right, that that these 2 add up to the original one. Okay, and this is we're going to use this to generate a kind of random walk expansion, except it will be sort of a block random walk. And but you don't even need to use it. You don't need to use it many times, but it will be instructive for us to discuss that case. So, any questions about the statement? What I mean by this resolvent identity, because it's actually quite important. And as I say, the advantage of it is. So let me just make one point. If I take my Green's function, g0, and I let x and y. And let's say x and y is x is here, and y is over here. Well, these 2 matrix elements don't talk to each other because they're separated. it's a direct sum. So they're in different spaces. So obviously this is 0 if the boundary separates x and y. Okay? And this is, actually, if you go back to Anderson's original paper, this is how he starts out with some kind of a random path expansion. And this will be a version of it, but except that I'm going to be using blocks instead of nearest neighbors and walking like that. So if I do this for a Laplacian, or a Laplacian plus a mass, I will be just generating random walk. What I'll be doing here is I'll be generating random walk, but my steps will be given by block Green's functions. That's all. Just block Green's functions. So I will call this a block resolvent expansion. And so it's a very simple thing. And it's better done on the lattice than the continuum, but you can do the same thing in the continuum. It's just then you have to take the normal derivative along the boundary and integrate. So there's a completely analogous theorem for that case. So now let me, I can erase this now. And so let me show you just a little bit, because I think it's instructive. Many people like to have sort of a path picture of localization, and this is, you can't usually write Feynman integrals for these things, but well, I guess you could, because this is discrete, but somehow these are kind of this is the closest thing I can come to finding a Feynman-like integral, except it's really a discrete path sum. So here's what
So is this meant on average, or?
Nope, not average.
So why are these 2 points actually uncorrelated?
They're really, you see, yeah. So that's I'm glad you asked me that question. Okay. So if I make this, if I think of this as a big matrix, okay. So just think of this guy here as a big matrix. Really, what you should think of is a matrix that looks like this. Here's my matrix, and I have a block here. This would be B, and I would have something B complement that sits out there, and over here I would have zeros. Okay.
Yes, but well, what does actually a boundary operator mean? Is it just a potential that is?
So this is just a matrix element.
Yes.
Okay, and this matrix element is only see this. What I've done here, which I didn't explain this part better as well as I should have.
My question is, why is there actually no kind of tunneling through the wall?
Yeah, you can't have it because I've cut it all out.
You said the matrix element is 0.
I said all the matrix elements.
Tunnel if there's no matrix element.
There's no matrix element coupling any of these guys. I put all those matrix elements over here, and I just reorganized the integral.
So literally decompose your system.
I just literally, by brute force, decompose it into pieces. Okay?
Of course,
Yes.
it's just G0. He's going to compute G.
Yeah.
G will connect.
Yes, G will certainly connect. But this is G0. So notice this is G0 here.
Maybe you should stress that X is inside B and Y.
Yes, I drew it here in a picture. X is here, and Y is out here. If they're both in here, you don't get 0.
So maybe if you draw the picture of G1,
G1.
or H1 rather, then you'll see that the
H1 is the guy that connects these two, right?
Yeah.
So there's an H1 over here, or gamma. Call it gamma. The gamma is the guy that connects them. But I've set that equal to 0. Does that answer your question?
Yeah.
Not entirely, I guess.
Let's just go on.
Yeah. So no, it's like if I have a matrix, if I have a let's say a matrix like this, and just think of it as a 2 by 2 matrix, and I have something A, B, C, C over here. So I make it a symmetric matrix.
Yeah.
And I drop my C's, which is what I'm doing. Then anything over here and anything down here, they don't talk to each other.
So I know
It's always. It's a direct sum.
Gamma refers to that you label your lattice in such a way that all the first indices are.
Yeah. All the indices, they're labeled geometrically. Really labeled geometrically. They're labeled by indices that live inside and indices that live outside. So in fact, this gamma, this Laplacian, is really a direct sum. It's a sum that lives in here, and there's a sum that lives outside. So it's a direct sum of 2 pieces. And the coupling between the pieces just comes from this.
So written
it's not direct, it's orthogonal.
Yeah.
The matrix you've drawn there is for H rather than G, is that right?
That is the matrix for well, yes. Let's say yes. H. That's correct. Thank
So
you.
written in this basis, your Laplace gamma had quite a complicated shape. Isn't it?
Laplace
Or still this-
gamma. Laplace gamma. Yeah. So let me make sure that this is clear. Laplace gamma would be this one, but the gamma equals 0. So that's. So in other words, that's the one that I've. This means I should say. This means I've taken the gamma out. I could put a sub b in here if you wanted to, but that's maybe a little misleading because I wanted to have matrix elements out here too. So this guy is a direct sum of inside the box and outside the box. Okay, with no coupling in between, because that coupling's all sitting in this boundary term. Is that better? Yes. Okay. All right. So we'll move on, and so this is a simple enough thing, and I think what people used to do before Anderson was to expand the Laplacian, expand this about the Laplacian, okay? And that's still not a bad thing to do under some circumstances, but when you want to understand localization, this is not such a bad thing to do. Okay. All right, so let's iterate this. Okay, let's just iterate it a couple of times. I'll draw a few pictures. I don't want to draw all the. So we have now, yeah. So let's just do the first one. G0 x y. Gxy. I'll write it out in matrix formulation. Equals G0 xy. And now I'm going to tell you that's 0 because I'm going to separate them. I'll draw the pictures, and so hopefully it'll be clear. And then I have a minus. No, actually I'll have a plus. The sum of g of xj, gj prime, y. And that is the result. And I know I had a minus sign before, but don't forget this thing has a minus sign, so when I do that. And this, what does j and j prime run over? Well, j and j prime runs over the boundary of my ball. So j and j prime are the matrix elements that live over here.
One of them should have a 0 index, right?
Yes, I probably lost my index. This one needs a 0 index, okay? Or the other one. You have your choice. Yes, thank you.
Minus.
It is plus because it's plus.
Oh, yeah.
It's plus.
And you could just
I usually make those mistakes, but not today. Yes?
You can put a gamma in between and don't.
Yeah, I can put a gamma in, but I can do that and then sum over everything. But I think it's better. I don't want to put the gammas in. Maybe I should put the gammas in. It's the same thing, of course. And then Martin's minus sign would come in, and then I have another minus sign and cancel it. Anyhow, so now let's do this again. So let's take this guy and do the same trick on it. Just do exactly the same thing. Okay. So look, we start. Here's x. Here's y. Far away. And then if I do that, this term goes away for reasons we just discussed. It's just 0. It doesn't matter what your potential is. These resolving identities don't care what I have do no averaging or anything at this stage. These are just identities. So here's my first ball, which I call B. Now I'm going to draw it as a circle because it looks a little nicer, maybe a little faster to draw. And here's my J, and here's my J prime. Now this guy doesn't. This term here is nice because it just lives in this region here. And I would like to be able to do everything in finite regions. I'd like to be able to re-express everything as a sort of a sum of finite things. Of course, I'm not going to entirely succeed in doing that, but I'll make an attempt. And this is a J prime here. Okay. So for this guy, I will repeat the argument, and I have to pick, depending upon the J prime, I have to pick another ball. So given this x, I chose this ball here, or a box. I guess I called it B. And now for this one, it's nice to have something doing this. So why am I choosing these large boxes? Why don't I take something small? Because I'm really interested in some kind of macroscopic distances. So how I choose this ball is up to me. But if I want to do something kind of interesting, it's better to pick the balls not too small, not too big. small enough so you can control them, and large enough so that you can see some of the physics. So then you repeat, and I mean, if I call this J1, then I'll get some other point here, J2, J2 prime, and I repeat. So, and then I'll draw another ball around that.
I thought you were going to partition, but you're not partitioning.
I'm not partitioning. Partitioning,
What
you
is
could
the meaning of
partition.
the balls then? What's the meaning?
Yeah.
It's not the picture you draw originally.
Yes, it is, but I have to do it again.
You don't have to introduce.
So this, I think everybody's happy with this formula, okay? So what I'm going to do is I say, well, listen, I'm still not happy with this formula because I've got all this stuff over here, which I still don't know anything about. So, but maybe this point might be a little closer to y or something, okay? In any case, I felt something of the physics at this scale, okay? So now I just wanted to repeat that, but when I repeat it, I have to repeat it with a ball depending upon J prime. So here, this was my initial ball. Maybe I'll call this B, and I'll call this next one, and I can choose it as I like. It's up to
When
me.
you draw the ball,
You redraw it.
the thing is that every time the line crosses a link, I'm deleting that matrix.
That's right.
What you mean?
Yes, that's what I'm doing. So then I just take. So let me just do it explicitly. I have J prime, y, and then I write this. Now maybe it's bad notation, so I'll put a G0 prime on this J prime y. That would still be 0, right? So I just repeat the same thing up here with another ball, which is this one I've drawn here. Okay, it only sees as J prime, and I repeat the same thing, and then I will get so I'll have this one plus G J. Let's call it this J1, and then J2. Excuse me. G0, and then J2 prime y.
And the things I deleted at the earlier time, they remain deleted.
Yep. Well, they don't remain deleted in here. They do not remain deleted in here. They remain deleted here, and but the G0s, the G's still are full.
Okay.
They are still full.
G is always the full grid.
As all, you can do deleted ones too. If you wanted to, you could do such things. I'm not doing it here. In fact, it's useful to do deleted ones. Yes.
The summary should be also J0 prime, right? Yes.
This is over the boundary. This is the boundary over J2, J2 prime
The resolvent
belong
should
to
be
the
prime.
B, what I call it. Now I should call this one, I call this B. I guess I'm going to call this one B prime, okay? B prime. And so then I repeat again. I repeat again and again, and I get a path of balls, right? It's like a walk, except it's a generalized walk. Sorry.
The resolvent should be primed as well.
The resolvent should be primed as well. Technically, you're absolutely right. Yes, because it's a different ball. Mm-hmm. Yeah, and to do it with all the notation proper, it might be a little cumbersome, but the primes should definitely belong there. But then really I should say, which J it was and so forth, so it gets a little archaic. But the idea is simple enough, it seems to me. So you just repeat the same thing, and your choice of balls is up to you. You can choose them as you like. Typically, you want to choose them so that you know something, or let's say you know something at some scale, and you want to get some information at some larger scale. So you start patching up the information you know at some scale and see what you get. So is that clear? So let me make a little comment. So why such a thing is kind of interesting, and how things like this actually give you bound on critical exponents in other systems. So it seems like such a simple matter that it wouldn't have much interest, but let's see what we can learn from it. So this technique is used in statistical mechanics for Ising models, rotators, even disordered ones. And so let me tell you what it says in statistical mechanics. So in statistical mechanics, it says if I take a spin correlation, sigma 0, sigma x. So this is an Ising system. It can be at critical temperature if you like. And then I'm working in some box lambda, or B I should say here. And I'm going to sum x over the boundary of B.
We're lost because we we don't know what's the resolvent identity.
Ah, resolvent identity is what I've written here. And what it is over here. Yeah, I'll yes, of course. I will tell you. Maybe I will tell you what it is. So this is, so sigma 0, it's almost the same thing, equals B. If B separates them, then it is the sum of sigma 0, sigma j prime, sigma x, and then sum over the boundary of B. This is not an equality, as it is in our case. It's an inequality in Ising systems and rotators. So it's very similar. If you notice, the structure is almost the same. This is like 0j. This is my G0. And I should have a boundary on here. Okay. Sorry, this is the full one. Excuse me. Okay. That is not the resolvent identity. This is what's called a correlation inequality. And we have an identity instead. Okay. So sigma 0, sigma x, plays the role of G0x. Sigma 0, sigma x, in a box B, plays the role of G0, sigma 0, sigma x. So you cut the system off. So this is in a box, so I don't feel the outside. And so this is, so now let me finish the statement. If this guy is less than 1, strictly less than 1, okay, then you have exponential decay of correlations.
Because you can iterate the argument, and every time you win by something a little less than 1.
That's it. That's all. Okay. So what does that mean? That means you cannot have a power law which is, if your power law is faster than 1 over r to the d minus 1, then you will actually have to be exponentially decaying. So it tells you that you cannot decay too rapidly. If you decay with a fast enough power law, you decay exponentially. Okay? So it just tells you some bounds on eta, for example. It can't be too big.
Didn't Huygens do this first?
Hmm?
Isn't this really Huygens' theorem in a way?
I don't know. It's
Probably the first.
Is that right? You need these correlation inequalities. Okay? You need the correlation inequality. Now, for us, it's an identity. Right? But the trouble with our case, so the reason I treat this case first, is that our system is not homogeneous. This one's homogeneous. Okay? So you can't quite apply what you want to the Green's function because you've got a random potential in there, and whatever you might say might be true on average, but it might not be always true. So you can't, if you want to do something interesting, you have to do something more. So once you have a spin-spin correlation, so the moral of the story is, if you know enough about the system in a box, and you have an inequality like this, you're finished. That's the end of the story. As Martin said, you simply repeat it again and again, and you get a factor less than 1 every time, and it's important that it be strictly less than 1. And you just get powers. Let's say it's a half. Then I start from here. I start from 0, and I end way out here at x. And I just have to keep on doing this. And eventually, how many times do I have to do it? Well, you can figure. You just count the number of balls, the minimum number of balls it will take you to reach over there, and that will give you the correlation length of the system. Okay? I mean, it's an upper bound. It's not. It's a bound. It tells you that it decays at a certain rate. Okay, it's not sharp. It would be nice if it were, but it's nowhere near sharp. But it's not bad. And okay. So let me. So what I'd like to do now is to tell you something analogous to this. So this is statistical mechanics, not properly part of what we're talking about, but of course it is the motivation for what I'm about to explain. And because these things were known long ago. It's not quite so easy to do if you have inhomogeneous systems, because then you want to average, and then averages of products are not products of averages, so you have a little bit of trouble. But there's a way around it. And so now I would like to describe what are called finite volume criteria for localization. So there are two basic ones that to talk a little bit about. One is the one that was originally developed, and this is called multi-scale method, but it's now there's a much simpler version of it, which I don't know that I'll have time to get to, but it's a multi-scale method. And if you look at this thesis of Van Dreyfus, or one of my survey papers a few years ago, it's a fairly simple, it's an iteration of this idea. You just iterate this idea, but you don't know that this thing fluctuates. It can get large, it can be small. On average, you'd like to think it's typically small. If it's typically small, then the statement is in a box, then it's going to be small with probability 1 at large scales, because your probability gets better and your decay gets better. So it, roughly speaking, says that if I have G lambda, or GB 0x for some box is small, I won't be too precise here, with high probability near 1, okay, then you can actually deduce the fact that G0x decays exponentially fast to some rate, x minus y here, x here, with probability 1. There, I have to have some constant here, probability 1. Okay. So it's the same idea here. If I knew that these g's were all small, or all less than 1, I'd just iterate and iterate and iterate until I got enough powers of a half or whatever I'm using, and then I get something that decays exponentially. So if you know enough, but now if your localization length is very long, then of course you must pick this box at least the size of the localization length. The diameter of that box should be at least the size of the localization length. So if you want to see something, you've got to understand the physics at that scale, right? Somehow you have to understand that. Or you have to have some other idea if you're going to use this. So there's another, which is, I think, well-known and beautiful work that Eisenman and Molchanov started and later was improved with, it was fairly recently improved by Schenker and Hundertmark and some other people, Roland Friedrich, I guess. And they have a similar statement. And the version is the following. So this is another version of finite volume scaling. It says if, and now I pick my box B, if we know that the expectation of the Green's function 0x in the box B raised to the half power, I use a half, but you can use other things, and I sum here over the boundary of the box as usual. And outside here, I need some constant, which I won't try to make precise, but there is an important factor of the length of the boundary of B squared, I believe. And we'll suppose that this is less than 1. Okay. Now, you see here I said something about something being small with high probability. Here it's a little bit of a neater statement. It says that if I can compute the expectation of this in the box, and I know that it doesn't feel the boundary, that's the statement, it doesn't feel the boundary, then this implies, as A does, that you have localization. Okay, you get localization, you get dynamical localization, you get all the things you want to get. And so it just tells you that if I want to check localization, and it isn't too long, if it's a long length, as it will be in 2 dimensions, you're not going to see it with this technique because you won't be able to understand the box that big. So you have to have some other deeper idea. But if your localization length isn't too long, well, you just check your box and see if you can do the calculation. Sorry.
Yes, could you repeat again, please, what GB means?
GB, okay. GB, I guess I changed my notation, so I apologize for that. So that GB is like my G0, right? So GB is the Green's function restricted to the box, okay? So it's not restricted, it's with the gamma. So GB is G, well, I guess I call it G, what do I call it there? I called it G0 before, right? So it's G0, and that's with this Laplacian gamma here. And that gamma, that boundary would be the boundary of B, would be the boundary of that box. So let me draw a picture again. So here's the origin. Here's my box. And you have a choice of what box you would like to choose. And I'm summing over x's inside here. Here's my origin. And my Green's function lives in this box, B. So I take that G0. I don't know anything that happens out here. And notice this, an important thing. You have to put this half power. You have to put a power here that is strictly less. That's why it's called fractional moment. And this was the observation, beautiful observation of Eisen and Molchanov. If you do this, this is a nice quantity. If you put a power of 2 there, or you put a power of anything bigger than 1, that'll just blow up. So you have to. This fractional power is quite a useful tool. So it just says if I want to see localization, I just pick a box. And I compute the Green's function in the box, and if this is small enough. Now you see here you need more conditions. Unfortunately, it's not as neat as the condition I wrote down for the Ising model or the rotator. This condition is presumably way overkill, right? Probably much more than you need to prove localization, but unfortunately that's the best we have at the moment.
The idea you can pick the size of the box you like.
Right.
Perhaps you pick it, maybe it's too small and
Yeah. Then you're there, right? Yeah, exactly. There you go. That's right. You pick the box so that you can do, so that you see it's small. And if you can't pick a box and you can't do the calculation, well, you're just stuck, right? Then you may have an extended state, and then that's the end of the story. But if you're in the tails, for example, if you're in the Lifshitz tails, then such calculations are quite easy. Because why are they easy? Because it's very unlikely. So suppose I'm in the Lifshitz tail, down here somewhere. I'm down here. I know the density of states here is ridiculously small, especially for small coupling. Okay, that means if I pick a typical box, I don't have any spectrum in that box. Right? I mean the probability of finding an eigenvalue in there is essentially nil. Then I can use Combs-Thomas to get my decay. So you can use Lifshitz and Combs-Thomas to get the hypothesis and then deduce localization. I'm running out of time. So any questions on the philosophy here? So the philosophy is it's just very simple. It just says, look, you just cut the system up, and if you can control a cut-up system properly so that you don't feel the boundary. This idea, I mean, certainly in the mathematics literature, goes back to De Bruijn, and probably it's something every physicist believes is totally obvious. If you don't feel the boundary, then you know, just drop it, and the same thing will hold throughout the system. But it does require a little bit of effort to do, and even for disordered systems like a disordered Ising model or disordered rotator, there are analogous statements, but you do need this boundary squared or something like that to make it work. Okay, it's not an ideal theorem in that respect, because I doubt that that's really necessary.
Power 2 is related to the power 1/2?
No, I don't think so. No. The power of 2 it has to do with the fact that you have to decouple this thing a couple of times. Several times you have to see, I described a single decoupling where I just put one ball on. But then when you try to get so the idea is you want to get a recursion relation of this guy with itself, or the Green's function, get some running recursion. and you need to use this boundary operator several times. Every time you use it, you lose a factor of the boundary. So if you use it more than twice, you're going to see this thing. So the ingredient here is to use a resolvent identity, but you have to use it a couple of times. And then you have to have an additional trick, which I think I should put on because it is quite important. If you tried to prove this without knowing this trick, then you would probably be quite stuck. And this is basically the root of the Eisenman-Molchanov observation. So I think I will put this on the board. So the key observation in this fractional moment, I don't need that in what I'm doing, but this is for Eisenman-Molchanov and this method here, it's quite useful, and it's a very simple statement. It just says the following thing. I take the expectation, this is one variable now. This is one variable question of v0, and my random variable is v0 minus a to the 1/2 times, let's say, v0 minus b to the 1/2, v0 minus c to the 1/2. The expectation, let me call this fa, fb, okay. Then this is less than or equal to the expectation of fa times the expectation of fb. Maybe I should call this fbc. And there's a constant here. This constant is independent of A, B, C. That's what you need. And that you can check for various distributions. You need to know. You see, you can't use Schwartz inequality or anything like that. But the reason this is important is probably already been explained to you to some extent by the lecture of Leonid Pasteur, but I will reiterate it because it's so important. And that is the following. If I want to understand a Green's function, let's say G00, that's quite an important one to understand for the density of states and other purposes. Then I can write this in the following way. 1 over V0 times lambda minus some constant, which I'll call A to match up with my notation over there. Now A, I'm not telling you what A, well I can tell you what A is, but A is a complicated function, but A does not depend on V0. So you can extract all the V0 dependence by this little rank 1 formula, and there's an explicit formula for A, which I don't exactly remember. I think you have to drop the V0 in here and invert it. And this is a simple formula which I think Leonid wrote down, but anyhow, it's a good exercise to write it down. It's just exercise in rank 1 perturbation. Your V0 is rank 1. Okay, you can even find more complicated formulas for rank 2, rank 3. You can explicitly extract the potential dependence in your system. Okay, so that's more or less the idea behind. I'm not going to go into the proofs because I'm sure you're all pretty tired by this. We're getting toward the end of these lectures, and so I just wanted to at least sketch the ideas.
I do this, and then I sort of take it into 2 square roots.
Right.
And start processing.
Right. You package this inequality together with the fact that I need to control something like this and use a couple of resolvent identities, and you have to be a little bit clever. It's not totally obvious, but you can find this in this paper. I think it's around the year 2000 of Eisenman, Schenker, Hundertmark, and so this is a generalization. Probably the best thing to do is look at the original Eisenman-Molchanov paper, where you don't have to do much of this. You just do a one step and you're done. But this is the more powerful theorem because it really enables you to understand things from a block perspective. Yeah.
I have difficulty spelling the names you just mentioned.
Oh, sorry. Well, Eisenman number 1. So Eisenman. Molchanov. and then Schenker.
You robbed Eisenman of one of the ends.
Eisen. Yes, you're right. Thank you. Platonov, Schenker. There are more authors. Yes.
Perhaps I missed this before, but in this estimate you give, this
Yeah.
constant C,
What is the constant? It doesn't depend upon anything, okay? That constant C here is related to this constant that sits over here. And maybe some coupling. It's something that doesn't depend upon the region. So these things are actually, so localization for mathematicians, finally, after 50 years, it all seems fairly simple to understand what the mechanism for it is. What we don't understand, of course.
Tom, just to understand,
Yep.
but still it's somehow here is used that it's deep in tail?
I'm not necessarily using the fact that it's deep in the tail, but I am using the fact that the localization length better not be too big. Okay. If my localization length is too big, as it would be, in this two-dimensional system where we know it's absolutely enormous, this is completely useless, I would say.
Also close to transition.
Also close to transition. It's completely useless. Okay. It's only in tails or where the localization length is not too big. Okay. And then it works.
All of these are not sharp. You're giving something away, and
You're giving something away, but that's right. You're giving something away. I think that you can. Well, let me show you what you can do with it. There's more to do, and I don't know that I'll have time to really get through it. But let me get to the next part, which is basically a version of Fowler's scaling, a mathematical version of Fowler's scaling. So I mentioned this last time, and I will at least sketch how the proof goes. Another sketch. Okay. So you'll see it's not entirely useless, this idea. And of course, for any particular system, as I said, you don't want to be, but it has some theoretical value, I would say. And let me give you an example. So the example I gave last time says the following, that slow time evolution implies localization. Now, I made that precise last time, and I'll remind you again. Okay? And this is, at least as a mathematician, this is my interpretation of Fowler's scaling. Okay? So the experts here can tell me whether it has anything to do with it at all. It is close enough in spirit, so I don't think I'm too far wrong. So this basically...
this is subdiffusion implies localization.
Yes. So let's do A, one dimension. Well, no, first of all, let me remind you what I meant, okay? So I define this quantity r squared, Rm of t to be, and I'll say the expectation of it, to be the expectation of psi of t of x squared, x to the m, 1 over x, the spread of the wave packet. There's a 2m there, excuse me. And then we said this is going to be some constant, which could, of course, be m dependent. And then x to the 2m times a number, I guess I called it gamma last time, and I'll try to maintain that notation. Now, gamma is always less than 1. This is what I proved last time. Not exactly this form of it. I did it for m equals 1, but it's an exercise to do it in general.
What is x on the right-hand side?
X, oh, sorry, thank you.
E.
It is t. Yes. Okay. That tells you how the wave packet spreads, right?
And 2m should be m, right?
No, I want 2m to be, the way my notation last time was 2m was m. So when gamma is equal to 1, I have ballistic motion. Okay, x squared would go like t squared, x to the m would go like t to the m. That's ballistic motion. So gamma equals 1, ballistic. Gamma equals a half, that's diffusive, so forth. gamma equals 0, that would be localized.
Expectation.
There is an expectation. Thank you. Any other things I'm missing here? I'm glad somebody's awake. All right. So what am I going to show you? Well, what I told you last time what I wanted to say, but I'll reiterate it. And maybe I'll bring this board down. And I will only sketch it, but I think that's not unreasonable what I'm going to tell you. It's not hard to follow. So I'll do it in one dimension, and we'll see this as an analogous statement in higher dimensions. So in 1D, what I was saying is that if gamma is strictly less than 1, okay, and m sufficiently large depending upon gamma, that implies localization. That was the 1D statement. And the 2D statement is that gamma is less than a half. I would like to say gamma equals a half, but I cannot say that mathematically. I'll say if gamma is less than a half, that means subdiffusive. That implies localization. So, and there's a similar result in 3 dimensions. So the statement is if your wave packet evolves too slowly, it'll get trapped. Okay? And they're very simple examples of how this works. And if I have time, which I may have, depending upon how fast I can pass this next argument off on you, I will show you a model which is related to the model that Andreas Ludwig is talking about, in which these things are transparent, in my opinion. Yes?
Do you actually really mean equal, or shall you have an estimate lower or equal than Cm times T to the?
Here I mean, yes, I do mean less than or equal to. Yes. I do mean that. Okay. Yeah. Okay. Thank you. All right, so how do we do the proof? Let's do 1D. So what's the idea of the proof? It's extremely simple. And it's, of course, the basic idea goes back to Thales. There are many people who've been involved in this. Somebody was asking me for a reference. It's not so easy to find a good reference. The most recent work on this was done by Germinet and Klein in Duke Journal. They make quite a long story about it. It's very simple. It was also done essentially done in the thesis of Wei-Min Wang's many years ago. And then before that, I think it was done by, some version of it was done by Fabio Martinelli. And of course, before that, it was done by Thales and Anderson and all these people. So this is just the mathematics of it. So let me, here are the proofs. Okay, so I'm going to do 1D. You'll see the same idea works in any dimension. So in 1D, we want to translate information about the time evolution into information about the Green's function. So in 1D, we want to claim that epsilon is like 1 over time, which you can see from Laplace transform. And you can make all this quite precise, by the way. So I'm going to be a little sloppy here, but I hope you won't mind too much. And if it's too confusing, let me know. So then I claim this says the following thing. I look at the Green's function at some energy, E, and I will emphasize the epsilon dependence and drop the energy dependence. So I pick energy anywhere you like. It doesn't matter. And so the statement is here, I pick a 0, pick a box here, pick at the origin, and I look at the Green's function from 0 to x. So I'm going to pick from 0 to x. And I want this to be small, as you can imagine. So why is it small? Well, it will be small because of this hypothesis. Okay? So this will be small if x is large enough. So how big does x have to be? Well, it basically has to be bigger than epsilon to the minus gamma. And that's what that says. You see, you can divide this thing through, and you will then discover that this is small if x is, you have to choose the epsilon and the x in this fashion. Okay. So that's part 1. Part A.
Sorry, what is capital T?
Excuse me.
What is capital T?
T. That's the time over which you should be thinking I'm working here. The time scale. So the capital T is really the lowercase t here, but I might want to make it a little bit bigger to get myself a little room. So, okay, part B. So I'm going to rush through this, and then you can bother me. I'm going to claim that I can put this in a box of side G. Now I put a box in and I call it B. You can see where I'm going with this, I'm sure. This is small. And my box has to be bigger. The size of my box, L, again, has to be much bigger than, my size of my box, I don't want it to be too big. I want it to be, the size of my box, L, or the box side, I want that also to be of order epsilon. Okay. And that's still small. And my final statement is, and this is the one where dimension comes in, really. C. I want to be able to drop the epsilon in the box. I'm in a box, but I need to be able to drop the epsilon because I want these hypotheses that I described for finite size scaling to work. So I got to drop the epsilon. So this is, in some sense, the crucial step. And so then the claim is that I can replace this by, and absolute values in all these things, that GB, no epsilon, set epsilon to 0, 0x is small. Well, I can't say that with certainty. I can say it with high probability, as all these statements are with high probability. Okay. But that's enough. Once you know this is small, by the hypothesis sufficiently small, this implies localization. So the key step in some way is this. This has to do with level spacings in your box. Okay? Once I go into a box, I just have to worry about the level spacings in that box. And so let's see why it's legitimate for me to drop it. I think I've done it right. I won't swear to it. So once I have this thing small, by the arguments I was given, finite size scaling, I know I'm done. Maybe I have to put a square root, an average, or say it with probability 1, but the idea is that simple. And so this has to do with the Thouless notion of conductance. Thouless, and I think almost everybody, every physicist who works in the field, assumes that you have diffusion of some kind. Okay? And from that, they can then deduce that you really couldn't have diffusion. You might actually have to have localization. And that's what I'm saying, too. Okay? That's really what I'm saying, too. But unfortunately, we don't even know that the motion isn't super diffusive, right? I mean, I would like to say that. All right. So now let's do this part C, explanation of C. Okay. Well, I've gone from a box. So here's my spacings. I've got my eigenvalues. Okay. And here's my energy, typically somewhere here. And my epsilon is much smaller than the spacing. So what is my spacing? Spacing is, roughly speaking, 1 over the size, the volume of the box times the density of states, roughly speaking. Okay? So what I need to go from this step to this step without doing anything terrible is I need to make sure that the epsilon that I'm using is a lot smaller than that spacing, so it's invisible to me. So as long as epsilon is smaller than
by the box volume, right?
By the box volume. Right. Sorry, that's a B, right? Excuse me. I changed notations too soon. As long as epsilon is a lot smaller then 1 over the box size. I shouldn't notice it. Now, how do you justify such a thing? The answer is you do it with Wegener. And Wegener will tell you that with high probability, these two guys are about the same. Okay? Now, the box size, of course, will be, so to have this less than the box size, then if I'm in one dimension, then I can choose gamma equal to 1. If I'm in 2 dimensions, my box size has more, the eigenvalues are denser, and I have to worry about making epsilon smaller than that. So that's the reason for the scaling. So epsilon, so if L is the size of the scale, this is L to the D, and epsilon times L to the D, that's got to be much smaller than 1. And then you can justify the step. Now I'm saying these are small, small, small. There's always a statement in the background about the probability or about the expected value of these things with the square root. But since I'm running out of time, I don't really want to go into to all the little details. But let me just review the strategy again, because I think it's fairly simple. So first of all, we're making a very strong assumption here. Okay? We're saying something about the time evolution, and then we wanted to do something more about the time of evolution. We're saying if it's bounded by this, where gamma's too small, then in fact it's bounded by a constant, right? That's the statement, really. So you first, because all statements, it's probably, maybe you could do it directly with the time evolution, but it's not done that way. You translate the information from the time evolution into the information about the Green's function with an imaginary part. That's part 1. And then you will notice that tells you certain elements, Green's function elements, are small, provided x is very large. Okay? If in any case, if x is much larger than 1 over epsilon, this thing always decays. That's always true, no matter what. But now we're saying something more. We have a gamma here, which is strictly less than 1, or in 2 dimensions, less than a half. Then you say, okay, this is small. Then I can put, because of the scale of this thing, I can put a box of about that size around here, and I don't really change anything much. Then the third statement is I can remove the epsilon, and now I have the hypothesis that, roughly speaking, that tells me that I can deduce localization. So this is essentially the argument, and since I'm almost out of time, I guess this is probably worth reviewing in case people have questions, which I imagine they do. It's not a hard theorem. It's you just have to piece together things that are fairly easy, and you have to do resolvent expansions to check that when you put the box in, it doesn't make any difference, and you have to do some resolvent work when you have this epsilon. You have to use Wegener, but I just want to make the ideas, outline the structure of the proof, because I think it's simple, fairly simple. So any questions about this? So Martin, would you say this is close to Thalys' picture? I wanted to ask Thalys, but
Thalys, the way I understand it, he talks about sensitivity to boundary conditions.
That's right, but he relates that to conductance.
As a level spacing.
Right.
If
that's what I'm doing too.
One, we get into localization.
Right.
This is how I learn it. I believe that this has some relation.
Yeah, you can see that the level spacing is right in here, and the epsilon is related to the time scale I need to cross the sample. So I think it's quite close. I think it's quite close. Anyhow, that's the best I can do. So let me just, I see my time is up, but maybe there are questions about this, in which case I should try to answer those. I know it's late and probably. Yes?
When you wrote down this epsilon smaller than 1 over the size of the box.
Yeah. So that means this basically, right? That's this statement here. Yeah, that's the statement. Okay.
I think it's
He's asking, I guess he's
Sorry.
asking, how do you know that?
How do I know that? I have chosen L, the box. So this is true. In other words, if gamma is less than 1, remember my box, this L should be the same as this L. Okay? And then if you do it right, this is, for gamma less than 1, you would do the job because I'll have epsilon. And in general, I'll have epsilon to the minus gamma times the dimension. And that will have to be much less than 1 for small epsilon. So that's why the 1 upon d comes in, right? I mean, that's why you need gamma in 3 dimensions to be less than a third, and in 2 dimensions less than a half, and so forth. So it just guarantees that I don't make too much of an error when I drop the epsilon. The epsilon tells me what happens at certain time scales. At certain time scales, I know it's small. I just divide by the x squared here, x to the 2m. I know it's small. Then I say, well, I put myself in a box, nothing much happens. Then I take away the epsilon. Then I've learned something. Okay? So in fact, there's a lot of information contained in here. And if one knew, for example, that if I have a strip, and I knew, which I do not know, that my strip is uniformly subdiffusive in some sense, then I could easily get all kinds of bounds on Lyapunov exponents and all kinds of things, which unfortunately we don't know yet. But so this shows you the power that there is some power in this finite size scaling, even when you're looking at a theoretical level. Anyhow, this is a strong hypothesis, but it's one that every physicist makes, I would say. Yeah.
Where does the disorder come in?
The disorder comes in through this average here. There's an average here. Okay? And I need to be more specific about the probability of these events. This is not a statement which is true without averaging, because I can, as Martin pointed out, I can take my potential to be 0, and then I'll get ballistic motion. So it's definitely coming in through the fact that your particle is undergoing many scatterings.
And this is in spirit of, in fact, I think it's very, ideologically, it's very close to Taro's argument, because I see it slightly different than Martin. That he just compared the time needed for a classical particle needed to transverse the sample is quantum mechanical time h bar divided by mean level spacing. And
that's it. That's what I'm doing.
Yes. Basically it is.
Yeah.
Modification of this is to compare with the twist of boundary conditions. Just another way of looking.
So this was done, as I said, something very much like this was done in Wei-Min Wang's thesis, and then before her, I think Martinelli and some of his early work, and so it's been sort of kicking around, but it's never, nobody's ever made much publicity for it, I could say. So it's so I sort of thought it would be worthwhile explaining here. Okay, now what do I want to do next time? Well, I didn't get to 3 pages here as usual. What I wanted to do in the next time was to just explain how physicists understand diffusion and localization in 2 dimensions through ladders and cross ladders. But probably I won't spend too long on that. That's fairly standard material in any text. And I will explain another perspective, which is, I think, very, I find it very illuminating. It's this work on this hyperbolic nonlinear sigma model that Martin invented many years ago. And in this model, I just want to reemphasize, you can see localization, delocalization. You can see localization in 2 dimensions. You can see a localization, delocalization, transition. I'm not saying you can prove all these things right away, but they become transparent even at the saddle level. Just the nature of the saddle will reveal all the things that Jan has been trying to explain to you in a more complicated model. This is a simpler model, and you don't have to do, you don't even have to do perturbation theory. You just have to study the saddle and see what it tells you.
Yeah, question like that?
Will you give any argument or any rationale for why you think the saddle is particularly appealing? I mean, for a mathematician, I want to know how much math you think is in the statement that he just made. How rigorous a statement
Yes, okay.
you can.
Now you're asking tough questions here.
Because it's just a saddle, that's right.
It's just a saddle, absolutely. Now usually, you know, when you look at the sigma models, you have to go beyond saddle. You have to go one loop and so forth. I have a short answer, which is that in 3 dimensions we can control the fluctuations around the saddle as long as
connectivity is large enough.
Connectivity is large enough. So we have control.
Pair connectivity large enough, and we have control.
Now, what we actually don't have, which is embarrassing to say, but maybe amuse you, since we've been talking about localization, it's clear from the saddle that you do have localization, but we don't at present have a proof of it in this model. So this model is sort of kind to us at the extended end in 3 dimensions, but it is a bit nasty and not totally trivial to understand the localized side, although it's certainly there. And Martin, of course, in his original paper, proved that localization occurs in 1 dimension and computed the localization length. But you can also see from the saddle that it's localized in 2 dimensions, and so that's what I'll talk about. No proofs, just some sketch.
Okay, so we have T, and then I believe the last of the research center. I forget who the speaker is. Okay. So, and the subject of the talk is?
It's two-point localization.
Okay. Be back at 4 o'clock.